All right, hello and welcome to the short video on the introduction to differential equations. Um, Differential equations are extremely general. The definition is very broad. It is literally any equation that involves a function f and or one or more of its derivatives. That means that differential equations take the form of all sorts of expressions. Let's just give some quick examples to see. Y double prime equals y plus 3. So that would be an example. Again, it's involving an unknown function, y, and in this case, one or more of its derivatives. Let's do another example. We could have y prime equals sine of x. Again, this involves a function and or. That's the key. So it just has to involve the function y or any of its derivatives. And one more example, maybe y prime plus xy equals e to the x. Again, involves the function, and in this case, and its first derivative. The order of a differential equation is the highest order derivative that occurs. So this would be second order. This second equation would be a first order, and this one also a first order. And again, generally speaking, the order of the differential equation determines how difficult it is to solve, or what a general solution is going to look like. And on that note, there are a couple definitions in the section that you're going to need to know. One is what it means to be a general solution to a differential equation, and one is what it means to be a particular solution to an initial value problem. So when we say that something is a general solution to a differential equation, well, frankly, why don't we just pick a differential equation? This one is going to show up on the homework, but we're going to give you the answer. Actually, interestingly enough, with the next section, 7.3, you'll be able to solve it. But let's take a differential equation, which looks like the form y prime equals ky, where k here is some constant. And notice that all of these things are implicitly considered to be functions of x or t. Again, sometimes the x shows up, like here or here, and sometimes it doesn't. So even here, what we're talking about is a function of x, but we're talking about it's a function of x, sorry. We're talking about a function y, which is a function of x, but we're talking about some relation between, in this case, y double prime and y itself. So in this case, we have that y prime is equal to k times y. And so it turns out that, and again, you'll be equipped in the next section to show this, that the general solution to this is y of x equals c e to the kx, where c is some constant. And in fact, any constant will do the trick. What does it mean to be a differential equation? It means that if I start with this expression and I take all of the derivatives that appear in the equation, in this case just y prime appears, but notice that if we were talking about, say, this example up here, I'd have to take a second derivative. So what's the derivative of c e to the kx? Well, of course, by the chain rule and the what we sometimes call constant multiple rule, we would get this, ck e to the kx. The c just sticks around, and now I get, by the chain rule, k e to the kx. Notice, however, that I can regroup that as k times c e to the kx, and c e to the kx was nothing other than y of x. This equality being true is why it's a solution to this differential equation. Notice this says the same thing that this did. So that's what it means to be a solution to a general solution to a differential equation, and it's called general because it has this c, and this gives us a solution no matter what value c is. But we can be more specific. We can take an equation, I'll pick a different one just for argument's sake. We can take an equation where we want to specify a particular point, and it's usually the value of the solution at time 0. And that's called an initial value problem. Again, the reason it's called initial value is because normally we specify it at time 0. Sorry, pause the video there to think of a better example or a different example so we can get a little more practice in. So let's look at the following differential equation. Y prime equals y squared plus 1, but we're going to specify that y of 0 should equal to 1. Okay, so y prime equals y squared plus 1, and y of 0 equals to 1. And it turns out that the general solution to this equation is y of x equals tangent of quantity x plus c. Let's actually check that real quick because it's kind of an interesting example. And again, like the other one, this is one that you're going to be able to solve and might even solve actually on the homework for 7.3. So y prime or y equals tangent of x plus c, tangent of quantity x plus c. That's going to be important. So if I look at this equation, I need to know what y is, but I do, and I need to know what y prime is. So let's go ahead and take the derivative. And we get derivative of tangent is secant squared, x plus c, and then technically by the chain rule there's a times 1, but I'm not going to write it. Okay. And so now what we're saying is if we substitute y prime, our secant value, and y, our tangent value, we would get, the key is, again, we need to get a true expression. I'll write it in a different color here. So we would be asking, is it true that secant squared x plus c is equal to tangent of x plus c, this is my y term squared, plus 1. Again, just to be very clear, we worked out that y prime was secant squared, so I went ahead and substituted in a secant squared. We knew that y was equal to tangent, so I went ahead and substituted in a tangent, keeping everything else the same. And the question is this true? And the answer is yes. This is actually one of those trig identities that you're not actually required to know, but for what it's worth, it follows trivially from the equation sine squared plus cosine squared equals 1. You get this equation by dividing everything through by cosine squared. So sine squared plus cosine squared all over cosine squared would become tangent squared plus 1, and 1 over cosine squared is secant squared. So this is a true expression, but now we want the specific value. So this is the general solution to this differential equation, is this family of curves, but now we want the specific value which makes this true. So let's take a look. Well, y of 0 is tangent of 0 plus c. Oops, let me write that so it's clearly a 0 and not a theta. Tangent of 0 plus c, which is the same thing as tangent of 0, but on the other hand, we wanted this to be 1. So 1 equals y of 0. So 1 is y of 0. Again, that's what our initial value is given to us, but y of 0 is, because we know what the general solution is, tangent of 0 plus c, which is tangent of c, sorry, my bad. So this is a tangent of c, 0 plus c is c. So what does c need to be? Well, tangent is equal to 1 when c is equal to pi over 4. That's not the only time, but it's one time, so that'll work for us. So here we're going to take c equal to pi over 4. And in fact, in general, remember, tangent has lots of problems. So we tend to think of it as being valued, taking the same domain you use when you think about arctan. We tend to think of it as being defined on negative pi over 2 to pi over 2, in which case pi over 4 is the only value that will work. And so what we're saying here is that the specific solution to our equation is y of x is equal to tangent of x plus pi over 4. This is the unique value, the unique function, which satisfies both this equation and this condition. And in general, that will be true for initial value problems as long as they're well behaved. The solution is indeed unique. I want to stop the share. I pause the recording. I'm killing it on technology. I'll see you in a minute for the worked example problem, where we'll do, I mean, frankly, the same thing, but maybe with a slightly more complicated example for after you've done the reading.